Hi students, this topic is about polar covalent bonds, chapter 2. So I was jogging at the Lower Pierce Reservoir in Singapore last weekend with my family, and this is a beautiful place on a Sunday afternoon, almost at the sunset. What you see here might be the clouds, the water, the lake, the trees, the greeneries, but what I see is actually many covalent bonds here in the rocks, ionic bonds inside the minerals, sodium chloride, granite, etc. So what are polar covalent bonds? Like the word suggests, polar means it is having a dipole moment. That means it is not symmetrical in terms of the electron cloud space. It is slanted towards one side. It's a bit imbalanced. And covalent suggests that there must be a sharing of electrons, bonding between nonmetals or sometimes between metals and nonmetals. So in this case, when you have a covalent bond, you see here two atoms forming a bond with two electrons between them. This is symmetrical because you can draw symmetry lines like a cross, you see, cross this way. So it is non-polar. However, if you have two different elements, X and Y, they have different electronegativity values, then in this case Y will pull more electron cloud towards itself. So now it's a bit imbalanced, although we can still draw a symmetry line here, but we can't draw this way. So you always have to have at least a cross in terms of symmetry level to be non-polar. So if you do not achieve this cross, that means it is polar. To be ionic, which means you have a total transfer of electrons. And how do you get ionic bonding? It is when the difference in the electronegativity between the two elements is so large that one of the elements wants electrons so bad, the other one doesn't want it. Take it. So you see, there's a total transfer. But when two elements bond together and one of them wants it so bad and the other guy also wants it, he doesn't want to let go of it, so what do? They share it. You see, so both are holding on to the same electrons, and hence you have sharing of electrons in these cases. And that's why covalent bonds and polar covalent bonds. So remember, bonding, the types of bonding, covalent, polar covalent, or ionic, is all about the difference in the electronegativity values. So in this periodic table, individually they all have electronegativity values except for the noble gases because they do not tend to form compounds. So what do we make out of these values? Basically, the higher the values of this electronegativity, the higher the tendency for this particular element to pull bonding electrons to itself. That means, like fluorine, highest value at 4.0, it wants electrons so bad, you know, that's the guy, when I see one electron, just grab it and stab it. Whereas on the other hand of the scale, you see cesium at 0.7 is one of the lowest value. Cesium, the least electronegative, which also means the most electropositive. That means cesium doesn't like electrons. It detests it, so it will just let go of electrons. And that's the reason why cesium is one of the most reacting metal, because metals like to lose electrons. And if I can lose electron, so well, then that means it's very reactive. So you see here, those in pink are the most electronegative elements, so you have to know the top four, okay? Number one is fluorine, that's the big boss. Then the deputy boss is oxygen at 3.5. Then the third boss is nitrogen, which has the same value as chlorine, 3.0, but nitrogen is a little bit more electronegative than chlorine because of its smaller atomic radius. That means the valence electrons is closer to the nucleus, greater attractions by a little. And number 4 will be chlorine, and followed by bromine. So like I said, you have to know the top 4 guys: F, O, N, and Cl. And you can see a general trend here. The electronegativity values will decrease down every group, and it will decrease from right to left in all the periods. So you see, you have a trend. That's in general trend, okay? So if I just tell you, okay, compare magnesium and barium, these electronegativity values, and I cover this up for you, you should tell me that, oh, magnesium has a higher electronegativity than barium. It's that simple. You might see some anomaly here and there, okay, but do not worry. General trend will be kind to you. You should get it right. So this is a picture to show what we call electrostatic potential map. It tells you about the region of space, about where you can find the highest concentration of electron density. So the red color means that you have a high concentration of electrons here, and this is not surprising because you have oxygen there. That's the most electronegative element among all the elements in methanol. Hydrogen, oxygen, carbon, these three guys, who's the best? Oxygen pulls electrons so well. And somehow you see the lone pairs of electrons here that's not used for bonding, surrounding this oxygen, two bond pair, two lone pair, there's a band shape, right? sp3 hybridized, and huge electron density in this. So we look at the difference between the electronegativity between the two elements involved here in the bonding. Oxygen, carbon. Oxygen stands at 3.5, carbon 2.5. The difference is 1. So 1 is not enough for it to have a total transfer of electrons, and hence it is a covalent bond. Now in methyl lithium, this is a very strong group 1 metal, your alkaline metal. The difference between carbon and lithium, 2.5 subtracted 1, you get 1.5. So 1.5 is almost on the cusp of having an ionic bond. So it's in between covalent and ionic. And you notice that the dipole moment, you see this arrow sign here? This is the dipole moment. It tells you where electrons are being drifted to. So in methyl lithium, since carbon is more electronegative than lithium, you will pull electron cloud towards the more electronegative element, so towards the carbon. Now conversely, in methanol, oxygen was the guy that pulls electrons, so it drifts from carbon to oxygen. We have something called the inductive effect, and this in chemistry tells you about the polarization of a bond. Polarized means, suppose normally, right, it is not polarized, it's like a lump, but then you can do something to it, right, to make it lengthen, elongate it, to change the shape, to make it asymmetrical. That's how we make it polar. So this works through the electron donating or electron withdrawing effect through the sigma bond. So it must be a covalent bond, must be a sigma bond. It's like having tug of war, just pulling electrons, right? Metals, like I said earlier, it donates electrons, it like to give it up. Non-metals like to take in electrons, and that's why in general last time you might have learned in junior school, you have a metal and non-metal, it should be a transfer of electrons, ionic bond. But we know that now at a higher level, the truth is bonding type is governed by the difference in the electronegativity. Like I said, if both of them wants to hold on to their own electrons, they will share. But if one want to give it up, one want to take it in, transfer. That's all it matters. Now, polar molecules and substances like to mix with polar solvents such as water. Here, I see a glass half full. You might say a glass half empty. I'm positive, so always think that way. Now, this is water. We like to mix with people who are like us. Like dissolve like. So you know that polar substance like to dissolve in and interact with polar solvents. So these are some dipole moments values. Again, do not memorize it. That's given to some compounds, general compounds. It is surprising that you see benzene here. This is very symmetrical. Not only I can draw more than a cross, I can draw 3 or more lines of symmetry. Can you see that? Follow my cursor. So it's very symmetrical. That means what? It won't tend to move if we have an external electric field. So that's why you have 0 dipole moment. So all the individual dipole get cancelled out. It is symmetrical. I want to put this way, but there's another opposing force on the opposite end. Same amount, so it's not going anywhere. Same for your ethane, methane, CO2. See, it's symmetrical. Just draw the molecule and you know why. Now for these other substances, they are all asymmetrical, so you see a net dipole moment. And in particular, see for NaCl, so huge, 9.00 dipole moment. Wow! Why? Because it's ionic. All the rest here, they are covalent. So you see the power of being ionic, total transfer of electrons here. Cations, anions, charged particles. whereas the rest here are just partially charged.